First lecture, we're going to be spending a bit of time here thinking about numbers and units in physics. In physics, we use mathematics as a tool. This is not a math class per se, and so the way we handle numbers have a lot of different meaning than it does in mathematics. Every number has an inherent precision to it, accuracy or so, and every number has a unit. Every number is part of a measurement or a calculation that comes from measurements. And it's very important that we properly express our numbers. We identify the amount of precision and accuracy in our numbers because we have a lot of context here. And so that's what the focus is going to be on in this first little lecture. I want to start with units. There's a lot of ways to express the meaning of numbers, and units are the way that we're going to do that. And there's various units that can be used for all sorts of quantities, but because this is a science course, we are going to be focused on standard units used in the sciences, which is known as the SI system of units. And what's nice about the SI system of units is that there's a single base unit for certain quantities such as time and length and mass, and other quantities are based upon those. And there's also a prefix system that's attached to the SI system that allows you to express larger or smaller quantities of a given unit without actually having to change the unit. And so the SI unit for time is the second, abbreviated with an S. And the strict definition of the second is not based on Earth's rotation or anything like that, which is commonly believed. We actually tried to make this as precise as possible, and it turns out that there's a particular oscillation of a cesium atom that's absorbed by that cesium atom can absorb a radio wave of a particular oscillation, which is a very precise measurement. In 1 second, these oscillations number in the billions, and as a result of that sort of very high number, we are able to put a lot of precision on units of time, and it's a very solid number. This 9 billion number, and that's important to have something that's really consistent in time. So, all right, our units for length is the meter. The meter is abbreviated with an M, and it's defined as the distance that light travels in a vacuum during 1/299,729,458 of a second. And this is because the speed of light, which is what that number is now a defined quantity. We don't measure the speed of light anymore. And when you combine the definition of the speed of light with the definition of a second, we have our definition of what the meter is. So that's what the meter is based upon. The SI unit for mass is the kilogram, not the gram, but the kilogram, which the kilo part of it is part of a prefix system, which means it's 1,000 of a gram. 1,000 grams, I should say, abbreviated kg. The kilogram had a change in standard a couple of years ago or so. It used to be defined as the mass of a particular alloy of platinum and uridium. It was put into a cylinder, stored in a national standards in Paris. The problem is since that was constructed, the mass of that thing has changed in various ways. I think it had gone down for some reason, and there's a lot of reasons for that. And it's not a precise way, at least. The standard is off by micrograms, and if you need something that needs to be precise down to micrograms, then this is not a good standard to use. We've now changed it to be defined based on the Planck constant. The Planck constant is something that shows up in modern physics and quantum mechanics. But it's a more precise definition now because it's ultimately based on the meter and the second and another, and this Planck constant. So again, one of the nice things about the SI system is that we have a single unit that we can use. If we want to express larger or smaller quantities of a single unit, we have this prefix system. And you see in the table here, we have various prefixes used. The ones for smaller numbers like centi, milli, micro, nano, these are pretty common. You'll see these quite a bit. Kilo is also very common. Moving into 120 and you get down a little farther, pico, faro, things like that. And there are abbreviations for those that get placed in front of the unit. Micrograms would be a Greek letter mu, which is what you see here, times g. Not times g, but mu g. And these prefixes, really, they correspond to just different powers of 10. And there's actually prefixes for every power of 10, but generally we don't need to use all of them. We usually separate them by 3 orders of magnitude. That's why you see milli, then micro, 10 to the minus 6, nano, 10 to the minus 9. So you definitely want to be familiar with these. Now, of course, we wouldn't strictly use prefixes for everything. I mean, would you want to describe things in gigaseconds? If you want to express a unit of time. So we don't always stick to strict SI units, but everything we do is ultimately based in SI. So there's other units we might use, for example, like the light year that's used in astronomy. It's not tactically an SI unit, but it is based on the speed of light, and it's based on the kilometer and the second, and so it's rooted in SI. So it's part of the SI system effectively then. But the thing is, we don't use the English system of units like is common in America. Things like inches and feet and yards. They don't have the same kind of consistency and convenience that the SI system does. And it's not as widely accepted, obviously, as the SI system. So these are the units that we'll be using here. And to be clear, units are important for a lot of things. I mean, it gives context to numbers, first of all. Second of all, it's important for solving problems. You'll see at the very end of the lecture today that we have something called unit analysis, where you look at a particular equation or quantity and you see if it makes dimensional sense. For example, if you have an equation that you think is supposed to calculate a volume, and you look at all the parameters involved, and you see that all the units come out to say meters squared. Well, that's not a unit of volume, it's a unit of area. So your equation is probably wrong, or the equation is actually meant for something else. So the use of units should be very important, and you really need to include units every time you express a solution or an answer. A number in a solution or answer without a unit is without context, and is not much you can really say about those things. So it's very important that you always include that. Now, unfortunately, there are a lot of situations where we are actually given English units, or we're actually given, units that are not really common for what we want to use for, so we have to convert them to things. And so unit conversions are a very important part of managing units. And the key to doing unit conversions is to use what we call conversion ratios. So if you see in the table up at the upper right there, we have several unit conversions. The top one says 1 inch is 2.54 centimeters. Now we can form a ratio out of those two numbers, as you can see at the bottom here. 2.54 centimeters over 1 inch. Now, while the actual numbers used to express these things look different, they represent the same thing. 2.54 centimeters and 1 inch represent the same length. So that ratio is ultimately equal to 1. Not equal to 2.54, it's equal to 1. Because you can't divide those numbers. It's apples to oranges kind of thing. They're different units. So, but what we can do is we can take those conversion ratios, and because they're equal to 1, we can multiply them by other units and convert the units to other things, so that actually changes the real value of the number. So, for example, we have an example down here of 2 feet, 2.00 feet. And we can convert that from feet into inches, inches into centimeters, centimeters into meters. And maybe it's a little long-winded here, but they did that with 3 conversion ratios. The first one went from feet to inches, and then from inches to centimeters with the conversion we just saw. Now, what's nice about forming the conversion ratios like this, the units sort of cancel out in sort of the same way that factors cancel out in fractions. And so it's a good way to sort of keep track of what units you're getting rid of and what units you're keeping. When you form the conversion ratios, you always want to form them in such a way that what's on the bottom is what you have and you're trying to get rid of. And what's on the top is what you ultimately want, either as your answer or for the next step in the conversion. Okay. And then when you actually form all these, what you do is you simply multiply all the numbers on the top and multiply all the numbers on the bottom. And if you need to divide, go ahead and divide. If you have numbers that are both on top and bottom, and you end up with your final answer. Okay. So let's look at a couple examples of this. See how this is done. Okay. All right, so, is this right? No, it's not. Okay, here we go. So we have 45 miles per hour that we need to convert from miles per hour to kilometers per second. So our 45 is in miles per hour. We gotta get the miles to kilometers, and we gotta get the hours to seconds. So we can multiply by 2 conversion ratios. The first one is 1.6 kilometers per mile. So I'll get rid of the miles to convert things to kilometers. And the second conversion ratio is 1 hour is 3,600 seconds. And that gets us from hours to seconds. So I multiply everything on the top, multiply everything on the bottom. Units of miles cancel. The units of hours cancel. And we're left with kilometers per second. And it does come out precisely to 0.02. But you'd want to state your answer as 0.020 kilometers per second or 2.0 times 10 to the minus 2 in scientific notation. And the reason why we're doing that is because of the use of significant figures. Our original number, 45, has 2 significant figures. And so as long as our conversion ratios have at least 2 significant figures in them, our answer can be rounded so that it has 2 significant figures. And I'll say more about that after the example here. To convert 15 inches squared to SI units, well, it says SI units, didn't really specify what unit, but because this is an area, and areas are based on length squared, we know that this would have to be meters squared to be SI. Now, because it's a squared unit, you have to convert both dimensions. So that means your conversion ratio, just from inches to meters, 1 meter is 39.37 inches, but we'd have to square that conversion ratio in order to get the square units of inches into square meters. So we perform that, and you could do this in your calculator. You get quite a number of digits, which we don't want to write all those down because that's just extraneous digits from the result of the calculation. And we have to, again, make sure we preserve the accuracy of the original number, which had 2 significant digits in it. So our answer has to be rounded so it has 2 significant digits in it. And the 9 and the 7 are the first 2 significant digits in that particular calculation there. I also wrote in scientific notation 9.7 to the 10 to the minus 3. Okay, so there's a couple examples of that. Now, as I hinted at here, we do have to could be concerned with significant figures when we do these numbers here. So just to be clear about that, every time you have a number with a unit, that number represents something. Say it was a measurement, something 6.2 meters. Well, the thing that you measured, maybe it was the height of something, 6.2. Is it really 6.2? Is it exactly 6.2? Maybe it was 6.19, and you just rounded to 6.2. In fact, it really could be any number between 6.15 and 6.25. Anything in that range there could be rounded to 6.2. But there was some instrument used, apparently, that could only get down to the 1/10 of a meter. And so we can't say anything with more accuracy than 6.2. If we wanted to add another digit on there, we'd have to have an instrument that can measure things more accurately. So as it stands, we were presented with this number here. 6.2, however, has 2 significant digits in it. So you can't have anything that's more precise than that number there. Okay, Okay, maybe the actual length was more precise than that, but we need to do that. The importance of this comes into when we do calculations. And when you do calculations with significant figures, you have to make sure that you preserve the accuracy of the original numbers in your answer. Okay, and there are some rules for this. And the rules are what we call the weakest links. And there are rules for addition and subtraction, and there are separate rules for multiplication and division. Okay, so first of all, when we do things in scientific notation, that can help us do more precise counting of significant figures. For example, we may be presented with a number 0.00620. Now, the way it stands, that number has 3 significant digits in it. The 6, the 2, and the 0 at the end. The 0 at the end doesn't look like it needs to be there, but it's explicitly placed there, and it's meant to indicate the value of that number there. Now, the numbers in the zeros in the front are what we call leading zeros, and the only reason they're really there is to place the decimal somewhere. And they're meant for magnitude. And we don't always want to write those zeros because it can be very tedious to write them, especially if our numbers are very, very large or very, very small. So 6.20 times 10 to the minus 3 would be the number in scientific notation. The decimal point is moved from where it originally was to be between the first and second number. That is considered significant. And then your exponent on the power of 10 is however much you had to move the decimal point. You moved it to the right by 3, so we get a negative 3. If we move left, for example, larger numbers, then it would be positive. Okay. So one of the useful things about this is we're removing ambiguity when we have numbers written, and we don't know how many significant figures they have. For example, the number 320 down here. Now, there's no unit on this. I don't know what this number represents. And if it's a measurement of some kind, I'm not sure if that 0 is meant for value or meant for magnitude. Is it meant to tell me the number is 320? Or is it meant to tell me that some quantity is precise down to the ones place? I don't really know. But if I were to write in scientific notation, 3.20 times 10 to the 2, I've just now clarified. Okay, so if I was able to write it that way, I'm communicating that the 0 ultimately did not matter. Okay, and it's true at the number at the top there. If the 0 didn't ultimately matter, we didn't have to put the 0 in the back here. We don't have to put it in the scientific notation. And when I rewrote the 320 here, like that. Now, if I wanted to make sure I emphasize that 0 is important, then I would have put 3.20. And then I would say it's 3 significant figures. But without any information, you have to assume that this is ambiguous, and you have to kind of assume the worst here, that there's only 2 digits. If you really want to say there's 3, you got to be explicit about it. Okay. So here are the rules when we do operations with numbers and significant figures. So for addition and subtraction, when you have a group of numbers that you're going to add or subtract or both, the number with the least accurate place value determines how you round the answer to preserve accuracy. So I have 3 numbers, as you can see here. One has 4 significant digits, one has 3, and one has 2. Now for this stuff, that's not something we necessarily care about, how many significant digits there are. What we care about instead is what's the place value of the last digit. We have thousands, we have hundreds, we have tens. That number, 4.6, is accurate to the tens place. So your calculator is going to tell you 14.868, but you can't write all those digits down. They have more accuracy than any of the original numbers. That doesn't make any sense. So we'd have to round that to 14.9. And the reason why I round to 14.9 is because we know that we are accurate to at least a tens place. Because all of these numbers had a tens place in them. So we can state that. Okay. And that would be the answer here. 14.9. All right, and it's determined by the 4.6 number. That tells us to round to the tens place. When we have multiplication and division, it's a little bit of a different rule. in this example, we actually do care about the number of significant digits, not exactly the place values for those digits. So when we work with multiplication or division, the number with the least number of significant digits determines how you round the answer to preserve accuracy. So we have the same numbers here, but we're multiplying now, not dividing, or sorry, not subtracting or adding or anything. And your calculator would tell you 94.83, yada, 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 yada. Now, the original numbers had 4 significant digits, then 3, then 2. 4.6 is 2. So we're going to round that number you see there to 95, because 95 has 2 significant digits in it, and that is the most we can have in our number to preserve the accuracy of the original numbers. So 95 would be the answer here when you round appropriately. Great. So I have a question for you here. Rank in order from most to least the number of significant figures in the following numbers. So you want to look at each one of these numbers and try to determine how many significant digits are in there. Think about that for a second. The answer here is A. So let's go through each one of them. 8,200. This is an ambiguous number. Could have 4, could have 3, but to be on the safe side, we have to say 2. Well, this number, we need more information to really determine how many significant digits are here. But so if we have no additional information, we err on the side of caution and we say 2. B clearly is 2, the 5 and the 2. The zeros in the front are not significant, therefore placeholder. For C, 3 significant digits. The 0 in the front doesn't matter because it's for the decimal, but the 0 in the back is an explicit 0. Doesn't look like it needs to be there, but it's been explicitly placed there. So we know that it is important. And of course, D, 4 significant digits. So the answer would be D, C, and then B equals A. Okay, so 4, 3, and then both the other ones have 2. Great. All right, we've got a couple other examples here. Let's look at those. Okay, we want to perform the following operations with the calculator, making sure to apply the rules of significant figures and write your answers on scientific notation. Okay, so each one of these, I'm going to first tell you what the calculator says, then we do the appropriate rounding, then we do scientific notation. You put number 1 into your calculator, you get 187.92. Okay, so that's obviously too many digits. If you look at your original numbers, you have 3 significant digits, and then we have 2 significant digits for 2.4. So that means we're going to have to round this to 2 significant digits, which 187.92 would round to 190. Now we want to avoid any ambiguity in reporting how many significant digits we have. That's why we want to write in scientific notation. You'd write 1.9 times 10 to the second power. Number 2, we get a very long decimal when we put this in our calculator. If we look at the original numbers, they both have 3 significant digits in them. So our answer was going to be 3 significant digits, 77.4. And actually, 77.4 is sort of fine. I mean, you won't really need to write a number in scientific notation because if you're not trying to specify how many significant digits are in a number by removing ambiguity in that, and you're not trying to specify a number that's really big or really small, it's not incredibly important to write things in scientific notation, but you're never wrong in doing it. It's maybe a good habit. So, but if I had to, and well, here's the third scenario. I tell you to do it. So, and in this one, I'm telling you to do it. So just do it. Anyway, it would be 7.71 times 10 to the 10. We slide that decimal point to the left 1, and then we have a power of 10 there. All right, the last example, we want to convert 32 kilometers per hour to SI units. So that would mean the kilometers per hour would have to be converted to meters per second, because meters is the standard SI unit for length and seconds is the standard SI unit for time. We start with a 32. We'll multiply that by 1,000 meters over 1 kilometer to convert into meters. We then multiply by 1 hour over 3,600 seconds to convert into seconds. Multiply all the top, multiply the bottom together, divide, and they get 8.88888 forever. Now, if we look at the original number we started with, 32, 2 significant digits. Our answer has 2 significant digits, so we can accurately say 8.9 meters per second. That would be the correct answer here. All right. The last example is on dimensional analysis. It's a little faded here, but a student is trying to remember some formulas from geometry. In what follows, assume that A is area, which is meters squared, V is volume, which is meters cubed, and all their variables are lengths, which is just meters. We want to determine if the following formulas are dimensionally consistent. So in the first thing here, we have V, which is a volume, equals pi radius squared h. That happens to be the volume of a cylinder. And if we look at the variable quantities, the r squared is going to be meters squared, and the height's going to be meters. So we multiply that together, we get a meters cubed, which is a unit of volume. There is a pi in here, but pi doesn't have a unit, so we have to worry about that. All right, so the next one, is this an area, this formula here? 2 pi radius squared plus 2 pi RH. That's what's being seen here, RH. And the first quantity there, 2 pi r squared would be units of meters squared. And the next one, the r times h, is also meters times meters, so it's just meters squared. So each term does correspond to an area, and so we add all that up, and we still have meters squared for that. Again, we're not trying to do any math here, we're just making sure that each term works out the same number of units, and both terms have meters squared in it. And this is right, this happens to be the surface area of a cylinder, so that makes sense. The next one here, we have a volume equals 0.5 B times H. Well, there's only two variables here, and they're both meters, so we get a meter squared. That's not a volume, that's an area. Next one is V equals pi times D squared. That's not a volume, that's an area, meter squared. And the last one is pi D cubed over 6. What is that? Surface area, volume of a cone? Volume of a pyramid? What is that? Volume of a pyramid? Is that what the 1/6 is? Come here, what is that? Oh, it's not. What is the volume of a cone? That's volume of a cone. I don't know what it is. Okay, I don't know what that is. It's something. Anyway, D cubed. That's meters cubed. That is a volume. Okay. It may not represent a particular shape. It can be something else, but unit analysis is a good idea. If you develop equations or you have calculations and you want to make sure that the number makes sense, a unit analysis is a good idea, or a dimensional analysis actually, where you just make sure that you're, if you're looking for a distance, make sure all your things multiply out to a distance. If it doesn't, well, something's wrong, right? All right, that's the end.